Hey, everybody, welcome to week 4 of NT160, Introduction to Nuclear Chemistry. So this is a fun week. This week we're talking about corrosion. And so we're going to go through what corrosion is, the different types of corrosion. So what corrosion is, let's jump into it. It's the deterioration of metal because it reacts with its environment. And there's lots of different ways that it reacts, lots of different mechanisms, so to speak. So in our nuclear power plant systems, that usually means water. It usually means oxygen, other dissolved chemicals, temperature, and flow. All these things matter. The metals corrode because they are trying to return to a more stable form, usually an oxide. Right? We try and force the metal into this, what we know to be this complete form. I have a little metal bar here, right? Like this, we try and force it into this. It wants to be a natural oxide state, its more stable form. So it's not just random damage. Yeah, it's just trying to be what it wants to be. It's an electrochemical process. And so why does it matter in a nuclear power plant? It can thin piping, it can damage components, it fouls our heat transfer surfaces, which all these can lead to higher radiation levels and then create reliability problems. So we can't eliminate corrosion completely, but there's lots of things we can do to help control it. So let's get into, I'm going to try this. Do we want bottom right or top right? There we go. We'll try bottom right today. So yeah, corrosion, metal deteriorates. It reacts with its environment. The metals tend to return to an oxide state, and the process tends to be electrochemical. All right, let's pause here for a question. All right. Because the corrosion is electrochemical, it means it depends on a type of charge transfer. And so you need an anode and a cathode. And this is where you have, and so once you have your anode, which is a negative, and your cathode, a positive, you need an electrolyte. You need some type of electrical connection. You need some type of oxidizing agent. So the anode here, the negative, is where the actual oxidation happens. This is where the metal is losing electrons. So when it loses electrons, so this little electron comes off, it becomes a metal ion, okay? And so it's losing metal. This is the actual metal loss. The cathode is where reduction happens. That's where the electrons get used up in a reaction, usually involving oxygen or hydrogen, O2 or hydrogen. And the electrolyte, of course, is the conducting liquid. So in corrosion, the anode is negative and the cathode is positive. The anode is the side being eaten away, and the cathode is what we call the protected side. So this anode is metal loss, and the cathode it's a reduction process, but it's a protected side. And then, of course, we have the electrolyte, which is the conducting water. And the more conductive the water is, the more oxidation you have, the more this electrolytic process you have going on. All right, so to draw this again, if I have a metal bar, and that's off. I have this metal bar, and the left side is my anode, which we said is negative, and the right side is my cathode, which we said is positive. Then we have electron flow. And that electron flow from the anode to the cathode, my electrons move from one side to the other. And so on this side, the anode side is where the metal removal, these metal ions are being pulled off. And so this is the oxidation side on the anode side, whereas the cathode side is the protected side. All right, let's pause here for a question. Hey, so like we said, oxidation is the metal losing electrons. So oxidation loses electrons. So the metal atom leaves the solid metal and it enters the solution as an ion, like we talked about. Reduction is the matching reaction, is that matching reaction where the electrons are consumed somewhere else. Like we said, we use We talked about hydrogen and oxygen as examples. It doesn't have to just be those. So oxygen and reduction always happen together. But we also had this thing called passivity. Passivity is different. It means the metal forms a thin protective oxide film on its surface. I was trying to think of an example of a thin protective oxide film on its surface. The one that immediately comes to mind is aluminum. Aluminum tends to form, and it's a very white, like you wouldn't think of aluminum of having a white powdery surface, but it kind of does, and it's just a natural oxide film that helps protect it. Most metals form some type of microscopic, almost dust-like protective oxide film on its surface. And that film actually helps protect the metal from further corrosion, because anything you can do to separate the metal from the environment helps protect it. So oxidation is the damage that occurs. The passivity is the protective condition, protective layer that forms to protect the metal from further corrosion. It can help slow it from damage. Now, there's another thing, polarization. Polarization also slows corrosion. And so this means one part of the corrosion reaction starts getting stuffed up, bottlenecked. The reaction still wants to happen, but it gets slowed down by limits. If I reduce the amount of oxygen in the water, I'm I'm producing a bottleneck. I'm slowing that reaction down because there's not enough oxygen to continue the corrosion process. If I cool the water off, because heat also adds to a corrosion rate, right? If I cool the water off, then I'm slowing down that corrosion. So polarization is just some way to reduce the corrosion rate. Slow, we'll say slow. Right now, my face I am slows the corrosion rate. So oxidation loses electrons for the reduction. That gains or uses the electrons. Passivity is a protective oxide film, and polarization is the corrosion reaction slowing down. Let's pause here for a question. All right, let's get into the different types of corrosion. So general corrosion is the one that we're most familiar with. It's just a broad, fairly even thinning of a metal surface. It happens because of little tiny small, if I have the metal surface here, right, and I got the metal surface, I have little small, change my pen color, anodic and cathodic sites. So anodic, and then we'll use blue, cathodic sites across the surface. All these things form and happen, and they keep shifting. Since the attack is spread out, no one spot takes all the damage. And so it just spreads out, and you get, like, if you think about iron, that's the rust, right? That's what happens. It's a bunch of anodic and cathodic sites all across the surface, and then you have that oxidation, which is the ionic metal removal, and it forms its oxide layer. So this is the most common form of corrosion, but it's not always the most dangerous. It's easier to see, it's easier to predict, and it's easier to monitor than localized corrosion. And the corrosion rate depends on things like temperature. Let's see, it's temperature. It depends on the flow of the water velocity, right? The more stagnant water is, the more time it has in contact with the surface and can do bad things, right? Oxygen content, the pH, dissolved solids, which affects conductivity. Yeah, and the condition of the metal surface, how smooth it is, right? How smooth or rough the surface is will affect how fast corrosion occurs, how likely it is to take hold. So the high velocity can strip away the protective film. So high velocity can be just as bad as low velocity. High velocity can take that protective, that passivization layer off. Oxygen makes corrosion worse, right? Which we've talked about just a lot. pH, if we have an acidic pH, it makes corrosion worse. The dissolved solids, that raises conductivity, which increases corrosion. Now let's talk about the pH real quick, because there's a band, and I think you see this in your PowerPoint. There's a band where over here in really acidic versus very non-acidic, very basic, there's a curve. Now you get a lot more corrosion when a fluid is highly acidic. But that doesn't mean there's no corrosion when it's highly basic. But if we were to draw that, there's a nice band, let's say right here to here, where it's stable, where corrosion is minimized. And I don't remember the numbers off the top of my head. Refer to your PowerPoint for the exact numbers, but off the top of my head, my recollection is roughly like 4 to 5 on the low end, and 11 to 12 on the top end, 10 to 12, 11 to 12 on the top end. So over here, you get higher corrosion rates. Over here, you get really high corrosion rates. All right, let's pause here for a quiz question. So we've just talked about the things that affect the corrosion rate. So how do we control corrosion? Well, we control corrosion by controlling the things that affect the corrosion rate. For example, pH. We already talked about pH. We control oxygen, total gas. We filter. So we have filters and demineralizers. What are those? What do you think those are removing? The conductivity, the particles, right? We get those particles out. We get all those corrosive species out. We use inhibitors. We use passivators. We use this noble metal chemistry plating. Another way to protect from corrosion, and we had this on submarines. We had to do this a lot as mechanics, is cathodic protection. So what that means is if I have a chart of metals, and I have metals that are more noble and metals that are more anodic, so noble being cathode, there's a level here, there's a line, and the ones over here that are cathodes are things like gold and titanium and platinum, and those are going to be the more cathode protected type metals. That's why you don't see gold rust. Gold doesn't rust because it's a cathodic metal. Ha-ha! Whereas we have more anode metals, and that's the more anode it is, the further on this way it shifts, the more corrosion you're going to see, the more active site corrosion you're going to see, the more metal will be given up. But if you have two metals and one of them is more an anode than the other, then the more anode metal will be the one that corrodes. And so the metals that are down here, the one that I know of, that I can think of off the top of my head, is zinc. Zinc is an extremely anodic metal. That means if we want to protect other metals, we want the other ones to act like a cathode so it doesn't corrode. We put in a sacrificial anode, a sacrificial zinc, because zinc is all the way over here on the extreme side of anodic metals. The zinc corrodes instead of whatever other metal it's in there with. And you'll see this if you have a water heater. If you have a water heater, every for a couple of years, there's a zinc anode in your water heater, and you're supposed to turn off and drain your water heater, pull this zinc anode out, and take it in, or go to Walmart or Home Depot or wherever and get a new anode and put it on there and put it back in your water heater, because that anode should be what's corroding to protect all the inside metal surfaces of your water heater. When people have water heaters that fail, one of the reasons is they stopped replacing those zinc anodes. So that anode is a sacrificial metal that corrodes instead of the metal you care about. Who knew you were going to get a home maintenance lesson as well? So this is also where water purity matters. The cleaner water means lower conductivity. Lower conductivity means less current flow, and that helps reduce corrosion. All right, let's pause here for a question. All right, now let's talk about crud. So crud, C-R-U-D, C-R-U-D, spelled just like it sounds, just as bad as it sounds. It's a corrosion product material. So in reactor systems, we get really, like we don't have big chunks and flakes of metal falling off of the inside of pipes, hopefully we don't. But we get really, really, really small wear products. We have these reactor recirculation pumps, and they have bearings, and we have wear surfaces, and it microscopic particles of wear that happens. And so these insoluble oxide particles go throughout the coolant. They're suspended in the coolant. They're moving through the reactor core. Sometimes they can attach to metal surfaces, but generally they move through the system until they find a place to lay down and rest. And so low flow points, valves, any type of restrictions, and they foul heat transfer surfaces because a heat exchanger, those tubes, it's a smaller, thinner surface. They lay out in those heat transfer surfaces and build up. They can clog flow paths if it's really bad, but usually we don't see it that bad. Like we see really, really low levels of crud because we keep the reactor coolant so clean. And then, but what that happens is in these low points of a system, like on a low pipe loop, or where a valve, where there's a little restriction and there's a valve and there's a little low flow spot and a little bit of crud builds up, they get activated. And so when it's activated, and for our PTEX, this is one of the things you'll be doing surveys in the plant for, is look for spots where crud is built up, because it will build up higher radiation levels. It'll build up a radiation level when it becomes activated, settles out in the system, and you'll see that increase in reactor coolant activity. In radiation levels. Now, let's say there's a transient on the system. So one of the things in a pressurized water reactor, they have reactor coolant pumps. They also have check valves. And if they turn off a reactor coolant pump, that check valve closed. And when it slams closed, that puts a vibration, a transient throughout the system, a pressure transient, a vibration transient, and that can shake loose that crud. So you see crud a lot more in pressurized water reactors than you do boiling water reactors. But that release, sudden increase in reactor coolant activity from the release of crud. So that's also a problem. And that crud, you think of it like sandpaper pieces inside the fluid, right? You put particles inside the fluid, high velocity flow, it'll tear off protective layers, it'll strip away the protective films and expose bare metal. So crud's bad. Crud can do a lot of bad things. Let's say it causes fouling, clogs, flow blockage, hot spots, not hot spots like temperature, hot spots like radiation. Radiation levels build up, and then you get higher activity. So conductivity, activity, higher activity levels in the coolant. And then this can cause your oxygen levels to change. It can cause your pH levels to change. It can cause your temperature to change. All these things, all those things can happen. Let's pause here for a question. All right, galvanic corrosion. Galvanic corrosion is, we've kind of already talked about this a little bit. It's two different metals. It's a type of electrolytic metal conversion, right? So galvanic is two metals in electrical contact with an electrolyte. So one metal becomes the anode and the corrodes faster, right? We did the whole anode, cathode, and this one side will corrode faster and create ions, go into the water. The other side becomes the cathode and is protected. So the less noble, more active metal is the one that gets attacked. So in this case, instead of one piece, just imagine this is two different metals. So the one on that chart I drew that looked like this, that had a line, and these are noble metals, and then it just kind of transitions up. So if you're on two metals that are on different spots on here, one will be more of an anode, and the more anodic metal will be the one that becomes the anode, and has the corrosion. So that's the bigger the potential difference between the two metals, and by potential difference, we're talking electrical potential difference. The stronger the galvanic driving force. Where do we see this? So we have piping transitions, we have fasteners, we have fittings, we have different places. We have lots of places in a power plant where different metals touch inside a wet environment. Now, we can reduce this by using two metals that are close together on this chart here, right? That are both kind of in line, and there's less of a difference between its anodic property and its cathodic property. So we use two close together. We can electrically insulate dissimilar metals. We can use sacrificial anodes. We can put a zinc bar in the system and sacrifice it and just have to change that zinc anode out constantly. We can control the surface area ratio. We can keep the electrolyte poorly conductive, which means pure water. All these things matter for galvanic corrosion. Two different metals touching each other with an electrolyte present. And then, so one of them will become the anode, one of them will be the cathode. And yeah, I think that's galvanic corrosion. Let's pause here for a question. All right, pitting and crevice corrosion. So pitting is a localized attack that forms small but deep holes. So if I have a metal surface here and I have a localized attack, and I don't know what I'm trying to draw, those are arrows. The attack keeps hitting this pit, and it keeps hitting the pit and gets deeper and deeper and deeper, right? It can form small but deep holes. It's dangerous because you can look at the surface and only see that much. But deep down, it's going all the way through. So it can look fine on the surface, but you get a tiny little pit and it's deep. It breaks down your passive film layers. It causes aggressive local chemistry. So chlorides are a big influencer in pitting corrosion. Low flow, oxygen differences, all these things help create the local electrochemical situation that drives that pitting corrosion. Now, crevice corrosion. Crevice is almost like pitting, but it's the environment, it's the situation that it's in that makes it different. So if I have how do I draw this? How do I draw something with a gasket? So I have a surface. Oh, shoot. So I have a flange. So I have a pipe, and I've got a flange here, and I've got another flange here, and another pipe. Okay. And water's going through here. But in order to put these two flanges together, I have to have a gasket between those surfaces. So on this, if I were doing an end view, it'd be just a circular gasket with a hole in it that goes around here, right? Well, what happens is you get these real low flow areas right here, especially on the downside of that, where the gasket might protrude into the flow area just a little bit, or maybe it's recessed and I got a low flow area right here on the end of the gasket. Joints, bolts, stuff like that. Oxygen gets depleted in these crevices. So crevice corrosion is you have these little crevices, little hiding spots, and it uses up that oxygen really fast, and it becomes aggressive. So this corrosion in these low flow crevice areas accelerates even while the outside surface, looks fine. So pitting is a local deep hole. Pitting is a localized spot on the surface of the metal somewhere, right? Whereas crevice corrosion happens in a shielded low flow crevice. They're both dangerous. They can both penetrate metal quickly. You don't get a lot of overall metal loss, mass loss, but that's what makes it easy to miss. And so, yeah, they're both dangerous. Even though they don't lose a lot of metal, they go through the metal in a way that you don't necessarily see. All right, let's pause for a question. All right, finally. Stress corrosion cracking. Stress corrosion cracking, you're going to see it often as SCC, stress corrosion cracking. It's the most serious form of corrosion damage in a nuclear power plant. So it requires three things at the same time. You have to have a susceptible material. You have to have a tensile stress. You have to have something with pressure, because you can't have a crack on something unless there's a difference in pressure between the surfaces. And then you have to have the right corrosive environment. So if I have a corrosive environment and I have susceptible material, and that susceptible material is under some type of pressure that induces a tensile stress. So if I have a reactor pressure vessel, right? I have a reactor pressure vessel. Imagine this is sealed up and it's 1,020 pounds in here of pressure. There's a difference in pressure from the inside to the outside. And so that's a tensile stress. So all our pipes are under a tensile stress. Our reactor pressure vessel's under a tensile stress. All our pumps are under a tensile stress. So we have a lot of places for that to happen. So for chloride stress corrosion cracking, the three conditions are chloride ions, dissolved oxygen, and tensile stress. So if chloride stress corrosion is a specific type of stress corrosion cracking. And it takes chloride ions, dissolved oxygen, and the tensile stress. That tensile stress is important because as that corrosion happens, and if this is my surface, and how do I draw this? And let's say there's a difference in pressure that's forcing it this way for whatever reason, and I have some corrosion happening here. So I get some chloride ions come in, and I start to have some corrosion. This will induce cracks because think of it like you're trying to bend something. And if you get little bits of corrosion, then you start cracking, it starts breaking down. I think that's am I doing a good job of explaining this? I hope I am. So the dangerous thing about stress corrosion cracking, especially chloride stress corrosion cracking, is it can cause sudden failure without a lot of warning, because you get all these little cracks building up throughout the metal, and then boom, it gives away because it's under a tensile stress. It's trying to deform, it's trying to bend, it's trying to, So stress corrosion cracking can cause contamination, cause loss of coolant, right? If it breaks, pipe breaks, you get a leak, loss of pressure. What we want to do is we want to minimize that tensile stress. We want to make sure we're choosing the right materials. We want to control the chemical environment. We want to avoid stagnant areas where chlorides can build up, where we can get aggressive chemistry concentration. So again, stress corrosion cracking requires susceptible materials, tensile stress, and a specific environment. For chloride stress corrosion, we're explaining what that specific environment is. You need chlorides, you need oxygen, and you need the tensile stress. And then, of course, the hazards: cracking, loss of pressure, loss of coolant, holes in the pipes, all kinds of bad things. Let's pause here for a question. Overall, corrosion is a group of problems. General corrosion thins metal. Galvanic corrosion attacks the less noble metals. When you have a dissimilar metal pair. You have pitting and crevice corrosion that attack really small areas really fast. And then, of course, you got stress corrosion cracking, which can cause sudden failures. And then we've covered crud. Crud connects corrosion to flow problems, heat transfer, radiation field problems. So the four ideas I want to leave you with: corrosion is electrochemical. Metal loss happens at the anode. Chemistry control changes corrosion rate. Localized corrosion is often the most dangerous because it's easy to miss and can fail fast. All right. That's it for the lecture. I hope you enjoyed this. Keep providing me feedback. Keep providing feedback. I'm going to try and keep doing these each week, and we'll fill up this NT160 with some actual lectures. All right. Take care.